Hello, this is lecture 5 of ML 223. So, as I said in the previous session, today we will try to understand something about functions from between subsets of R. So, in the previous sessions what we have seen is we are starting with the setup R with field structure, order structure, completeness property and all. Then just after defining the completeness property we realized the initial idea was to study all subsets of R and see if we can say something about this power set of R. This is the set of all subsets of R. Then we realized that if you want to use completeness property, we cannot do that for any arbitrary subsets of R. There is a condition between given two subsets of R. If they satisfy some condition, then I can use completeness property for these two sets. So this condition suggests maybe we should restrict our attention to certain special kind of subsets of R. Here it is a subset of PR, some special nice subset of PR. Then we came with some terminology, bounded above, bounded below, bounded. So this is that set of all bounded subsets of R is what we focused on. Yeah, so that's what we have done in the previous session. Now what we will do is we will try to understand set of all functions. Previously set of all subsets of R. Now it's set of all functions between subsets of R. So that is the main thing that we will be trying to do today. Now we are trying to understand set of all functions between subsets of R. So let U be a subset of R, and we will collect all maps or some maps that I mean depending on necessity we will restrict our attention, but for now we want to study all maps from subset of R to R. As a baby step what we will do is, see, the first collection of subsets of R that we know, right, are this N, right. Just after mentioning about the field structure on R, we came up with these three subsets, special subsets of R. So as a baby step we will try to focus our attention to the case where we study set of functions from this subset of R to R. This is the first step. We want to study we really want to study set of all functions between any subset of R. As a baby step we start here. So I was using this notation, I was using what, U subset of R. It does not mean it is a map from R to R, it only means it is a map from U to R, but this is only for reference, that I am trying to remind you that whatever U that I am writing here, it is subset of R, because U can be anything, it is not standard thing. So this is to remind that U is a subset of R. Then I said we are focusing our attention to the case when U is equal to N. Whenever I write N, I already know it is subset of R, so maybe I will remove this now and simply write N. So we want to understand set of all functions from N to R. Let us give a name for this. A function from N to R, we are calling it as a sequence in R. This is just a name, I mean. So a function from N to R, we usually denote that function by small letter a, small a, b, c and all. So we call such a function to be a sequence in R. Now let me denote set of all sequences by SR. Set of all sequences in R. So let me write down that sequences in R. This can be, I am just rewriting this, set of all functions from N to R. Okay. Now whatever I am going to say, this is not specific to set of sequences. In general, suppose we want to study some functions from a set A to a set B. Further assume that we want to study B is fixed, A is also fixed, and we want to study all functions from A to B. Now, suppose this set B has an extra structure, then most of the times it turns out that this set, the set of all functions, will have some structure that is inspired by the structure on B that we are starting with. Given a structure on B, this will inspire this set to have a similar structure. In the sense, let me clarify what I mean. R has a structure of addition, right? Given two elements in R, one can talk about addition of two elements. Similarly, let me denote this A comma B goes to A B. Yeah, this is slightly a bad notation. Here A comma B are elements of R. Here A is a sequence from N to R. So either I should change here or here. What I will do is I will not change anywhere. You should get used to the situation whenever you see the, I am not trying to support bad notation. Bad notation is bad, of course, but whenever the setup is clear, see, this is only notation. Whenever I write R cross R to R and write A, it should tell you that A is actually an element of R. You should not get confused that A might be an element here, A might be of this form. No, because I am already saying, right, R cross R to R. So yeah, this combined with this is a bad notation, but we'll still stick to this. Now this is a addition map. We also have the what map? Oh, this is not addition, this is A plus B is addition, right? And we have multiplication map. Similarly, we have additive inverse map. Given an element A, we have minus A. Similarly, given an element in this, we have A goes to 1 by A. Now what I am saying is the following: these maps, this addition map, multiplication map, the additive inverse, multiplicative inverse, these maps induce similar structure on this set. R was a set to start with, then we said there are some maps which we call addition, multiplication and all that. Similarly, this is a set. I am saying this set will also have maps of this form. Let me write down what is it. So SR cross SR to SR, the addition map. Now what is an element in, what was the notation for elements of SR? Small a, small b, small c. So let us simply take that. So A comma B goes to, here I should write something that should look like we are taking help from addition of real numbers. So when we are taking help from somebody, we should acknowledge them. So how I am acknowledging here is, I am writing the same symbol, right, I am writing the same symbol, and the symbol I have written, that is fine, but how do I define? A plus B is supposed to be element of SR, so it is a map from N to R. So an element N is mapped to something. How do I know what to write here? I mean, there may be many choices, but one thing that I should keep in mind is I am trying to use the addition property of R, and that is all I am trying to use. Now see, for an element N belongs to N, this element A in SR, what does it do? A is a map from N to R, so the element that I am starting with N will go to something, let me write as AN. Similarly, B will also take N to somewhere, let me write as Bn. These are elements of R. This An and Bn are elements of R. So in R I have a addition property. I can add two elements in R, so I will simply write that here. So an plus bn. Similarly, what do you think this multiplication should be? Same thing, n should map to somewhere. What I will do, I will just ask this person, where are you sending n to? They will say an. Where are you sending n to? Bn. I know the multiplication map in R. I will just use that. Simply write an bn. Then see, it may be slightly confusing to use this term. So let us change some notation. For a sequence into R, image of an element n should be, ideally we should be writing an, but just for convenience we will simply write as a subscript n. We will write a as a subscript, we write n. This is what we mean when we write a subscript n, we mean image of the element n under the map A, that is an. A subscript n is simply an. So just for convenience we are simply writing as a subscript n for an. The addition structure on R induce addition structure on SR. Similarly, multiplication structure on R induce the multiplication structure on SR. Now let us think about addition additive inverse. So R to R, A goes to minus A. Taking the experience of this into consideration, we should be able to guess that we are going to write what, SR to SR. A to minus A. Minus A is an element in SR, so it is a map from N to R. So what should I send so where should I send this element n belongs to n? I should just ask where does A take n to, it will take to an. Then we said just now that we are using the subscript notation instead of this. So we will write an with a minus sign. An is the image of n under the map A, then we are simply taking the additive inverse of the image. Now similarly, the multiplicative inverse map R minus 0 to R minus 0, what does it do? It takes an element A sent to 1 by A, if it is non-zero, if A is non-zero, then I can write down something like this. Now this one can try to do the same thing for SR also, SR to SR, and I want to write A goes to 1 by A. Now there is a small issue here. Here I am ignoring 0 element, there is only one element, that is 0, and simply saying that for every element that is non-zero there is a 1 by A. Here if I take an element in SR, there is of course a 0 element. What is it? It sends every element of n to 0, but there may be elements of SR which are not of this form, but let us say A is from n to R such that A of n is equal to 3 for every n not equal to 2, and A of 2 is equal to 0. Let A should be defined for every element of natural numbers. For 2 I am writing as 0, for any other element I am writing as 3, right. 3 is non-zero, so I have the corresponding multiplicative inverse as 1 by 3, but for this element I do not know what does it mean to say 1 by 0. So I need to be slightly careful here. Here if I ignore just the 0 element, this whenever I am trying to write down the multiplicative inverse for this, there will be an issue. I can write down 1 by an for every n belongs to n, but not equal to 2. For every n belongs to n, that is not equal to 2, I can write down this, but for n is equal to 2, this is 0, I do not know what does it mean. So for that reason we need to take some extra precaution and say that the 1 by A is defined for every element of SR with the following condition: there should be no element in N such that AN is 0. In the other sense, for every n belongs to N, AN is non-zero. If this is the case, then I can write down 1 by A for such A. So, I do not know if there is any notation for this kind of sequences. So, we will write down some notation, maybe SR star. This also might have different meaning, but for us SR star is set of all sequences in R with the following condition: for every n belongs to N, N is non-zero. Then I can talk about 1 by A. How is it defined? 1 by A of an element n belongs to N is simply 1 by An. 1 by An I can make sense if because An is non-zero. So, this is the structure on SR that is inspired by structure on R. R has addition, SR has addition, R has multiplication, SR has multiplication, R has additive inverse, SR has additive inverse, R has multiplicative inverse for non-zero elements, SR also has multiplicative inverse for for special subset of SR. Non-zero means anything that is not of this form, but we do not want non-zero. I mean, the phrase non-zero might imply we are ignoring only one element in SR. No, we are not ignoring just this, we are ignoring every sequence that takes 0 at some point. An is 0 for some n, then we are ignoring that when we are trying to write down 1 by A. This should be clear after spending some time. Nice. So, this is about sequences in R and how the field structure on R, the addition, multiplication, additive inverse, multiplicative inverse, how does they impose or how does they induce some structure on SR, that is what we have seen now. Nice. So, now what? As I said just now, we were trying to understand about subsets of R, which means this. Then we realized subsets of R, see there are two, the first condition is that this this completeness axiom, completeness property of the order suggests that maybe we should restrict our attention to certain special subset of PR. That is where the boundedness condition came. See, I can find this may be because of two reasons. First is maybe this is too much for us to study. So, studying PR may be too much. Second thing is, if I am studying whole PR, this suggests maybe we are ignoring, not maybe, we are ignoring the extra structure on R, the order structure on R we are ignoring. So, it is what is the point of mentioning the order structure if we are not considering subsets of that form. First thing is this too much for us to study. Second thing is we do not want to ignore extra structure, we do not want to ignore extra structure, ignore the here order structure. In general, in any other part of mathematics, this is what we will see again and again. If there is some structure, we want to consider the structure also when we want to study something. The order structure on R, I want to consider this, I want to take this into consideration when I am trying to study subsets of PR. Otherwise, I can just study it as a set, right. So, ignore the extra structure, Nice. So, now we were trying to do the same thing for sequence also. So, if I take sequence in R, I want to study sequence in R. What was the first idea? First focus point, we wanted to study set of all functions between subsets of R. Then as a first step towards that, as a baby step, we focus our attention to set of all functions whose domain is n, the set of natural numbers that we are calling as sequences, that is fine. But we wanted to study set of all functions whose domain is n, that is what is this SR is. Okay. Now whatever the same logic that we applied here, we should apply here also, because set of all the sequencer does not have any, we are not taking any other structure to consideration. When we are talking about sequences, we are not taking any other structure of R into consideration. So now let us take some structure into consideration. So one thing is clear, we want to study, take some structure into consideration and restrict our attention to this kind of things. Now the question is what should I restrict my attention to? If you don't remember, you can just go back and check to the previous session. After defining completeness, we focus our attention to the case to subsets that are bounded, either bounded above, bounded below. Something some nice things should be given to us, otherwise we cannot apply infimum, supremum or anything. So here also we are trying to do the same thing here. This is what bounded sequences in R. I will describe what is this, but the idea is clear, right? The same thing that we have done in case of subsets of R, we are doing the same thing for sequence in R. The reason is the same thing. We want to take into consideration of the extra structure of order. For that reason, we want to focus our attention to bounded sequence in R. Now, one need to understand the following. When we are describing bounded above, bounded below, there was a small issue when we are trying to consider the additive inverse, A goes to minus A, there was an issue. What was that? If A is bounded below, the obvious thing that happened is minus A is bounded above. There was some disturbance, it is not very clear why A bounded above should imply minus A is bounded above. What we get is A bounded above implies minus A is bounded below. Similarly, A is bounded below implies minus A is bounded above. So then we realized that this kind of thing is not behaving properly if I am allowing set of all bounded below, bounded above separately. Then one obvious thing to do is consider set of all bounded subsets of R, which is bounded above and bounded below. If I consider this, let me write down here, maybe I might have said the last time, but I am saying again. So if I take bounded above subset of R, if I am taking the additive inverse, this is landing me in bounded below subset of R. Similarly, if I am taking bounded below subset of R, this is landing me in bounded above subset of R. So these are different really. We have seen some example also that the n is not bounded above, n is bounded below. So this kind of things is not very comfortable to study. So then one nice thing to do is, okay, consider this set B is equal to BAR intersection BBR. What is this? Set of subset of R that is both bounded above, bounded below and bounded above. If I take this, then A goes to minus A. If A is element of B, what does it mean? It is bounded above. So minus A is bounded below. Very good. Because A is element of BBR, its minus A is bounded above. So once A is bounded above and bounded below, minus A is also bounded above and bounded below. So A goes to minus A is a nice map from BR to BR. Right, taking all bounded subsets of R was nice, is nice when we are trying to understand the additive inverse part. Similarly, same thing we try to do in case of bounded sequence in R. Right, now it is clear at least what is the reason to consider. See, here also I could have started with bounded above sequence in R, bounded below sequence in R, but just this suggests it may be a good idea to consider all bounded subsets of R instead of bounded above, bounded below. So here what we do is we consider bounded sequence in R, not bounded above or bounded below. What should be the definition? What is A? What does A does? A from N to R. If I take the image of N, which means the set AN such that N belongs to N, it is a subset of R. Right, I know what does it mean to say subset is bounded in R. What does it mean? There are two elements, M belongs to R, M belongs to R, this is small m, this is capital M, such that for every element in this we have the Praphulla property m less than or equal to an less than or equal to m for every n belongs to n, and this is what I am calling as bounded sequence in R. A sequence in R is said to be bounded if there are two elements in R such that the image, the an, is bounded by m and m. So let me write down this one more time. So this notation bounded subset of bounded R subset of SR. See, this may be slightly confusing. I am using the same symbol for both subsets of R and subset of sequence of R. I suggest it may be good to become comfortable, not because of the notation, but when somebody gives some setup, when I am writing a subset of SR, it should be clear that I am mentioning about subsets of R. If I am writing like this, it means an element here is a subset of R that is bounded. If I am writing like this, I mean an element here is an element here, it is a sequence in R that is bounded. So I am not saying writing bad notation is a good thing, I am saying notation should not stop you from understanding anything. So now we are focusing on this set of all bounded sequences in R. If you really want, you can just put some S somewhere, because I am dealing with sequences, you can put S here or here somewhere. Now that is about, we want to focus our attention from sequence in R to this special subset of SR. Now one should ask the following question. See, this SR has a structure, right? SR has a structure, whatever I mentioned just some time back. SR has addition, multiplication, a comma b goes to a plus b, a comma b goes to ab, an element in SR goes to an element in SR with a goes to minus a, an element in SR star, which means a sequence. What does this mean? A sequence that does not take 0 anywhere. An is non-zero for every n belongs to n. For such kind of elements, we have 1 by a. Now the question is the following. If I start with the assumption that a and b both are elements of this, does it imply a plus b is an element of this? If I take two sequences in R that are bounded sequences, does it imply a plus b is a bounded sequence? Right, this is a fair question to ask. This is the first question to ask, because this kind of thing you will see many times in mathematics. Let me write down. So assuming you know some group theory or some vector space, so let us take a vector space V or a group. I mean, it's only I am writing V, you can think of it as vector space or a group, whatever you want to think of it. Now we want to study some subset of V. Yes, it's a subset of V. Now the question is, S is nice only when the structure on V is inducing a structure on S in the following sense. Suppose we are talking about groups here. So let me change the notation slightly. So G is a group and B is a subset, H is a subset of G. Now what is the property of what is a group structure? If it comes with a group operation, with binary operation, G cross G to G. If I take two elements in G, I am getting an element in G. Now H is good, H is nice if the two elements that I take, if both are in H, the result will always be in G. The question is if it is also in H. For every AB in H, if A dot B is in H, then it is nice to some extent. We should also check for the inverse. If A belongs to G, which is an element of H, A belongs to H, then does it imply A inverse belongs to H? If these two are nice, then maybe ideally this should be called as subgroup of G, even if you do not know what is the group or subgroup, the idea is clear at least, right. If the structure on G, we want to see if the subset that we are choosing induce the structure from G, then we are calling H to be nice. Here the same thing, there is a structure on SR, we are trying to see whether it induces structure on BR or BSR, whatever, right. This is an exercise, you check by yourself that if I take two bounded sequences in R, the sum, is it a bounded sequence? If I take two bounded sequences in R, is a product a bounded sequence? If I take a bounded sequence in R, is the minus of that a bounded sequence? If I take a bounded sequence in R that is nowhere 0, is the 1 by a bounded sequence in R? This is the first set of questions that previously I did not mention any questions, right? No, I did not mention anything. Now, so that is about set of all bounded sequences in R. Maybe in the next session we will see some examples and all that, but before that let me introduce one more nice subset of R, nice subset of SR, nice subset of SR. Okay. Now the boundedness nature was useful when we are trying to do the infimum supremum and all that. So we were trying to imitate the same thing here also in case of sequences. Now given a sequence A from N to R, the image, this set AN such that N belongs to N is subset of R. So given two elements, say 1 and 2 or 3 and 4 in N, we have A3 and A4, these are elements of R. See, fair thing to ask is the following, in N 3 is less than 4, 3 and 4 elements of N, we know 3 less than 4, do we know that? Yeah, I am assuming we know that. I have said in the yesterday's class also, so 3 less than 4, nice. I am saying this sequence is nice only when this is reflected here also, in the sense A3 is less than A4, then that is one kind of nice sequence in SR, in R. Let me repeat one more time, 3 less than 4 in N, I am only asking the following question, does this property reflect at the images also? Is A3 less than A4, then I am calling A to be nice. See, nothing to do with less than, it can be equal also, for equal there is nothing to check, right. If 3 less than 4 is A3 less than A4, this has to happen for every possible relation. If M is less than N, this should imply AM is less than AN. This equality can, it is okay, here I cannot talk about equality, two elements cannot be equal. So but here the images may be equal, right, A3 can be 2, A4 also can be 2, who will stop me, right. So sequence in R with the property that the order in N display the same order in N, then we call M to A to be, then we call this kind of things to be monotonically increasing sequences. One can ask a slightly different question, suppose, see we realized that when we are dealing with the order property, order structure of R, this was not very nice when we are trying to do with this multiplication by negative element, the order is being reversed. If you remember, if I take A less than B and C is negative, then AC is greater than BC, the order is reversed. So reversing order is also, nice thing to happen, or maybe something that you cannot stop to happen. So we will ask the same thing here also. If M is less than AN, that I already have a name for this, right, monotonically increasing. So, maybe this is not true, but this is true. Am is greater than An for every m less than n. Then this kind of, if this is the situation, if this is, then this is called monotonically decreasing sequence in R. The name is clear at least, right? If this is increasing, so this is increasing, so this is increasing, so we are calling it monotonically increasing. If this is increasing but this is still decreasing, we call monotonically decreasing sequence in R. If the order is preserved, if A less than, if m less than n implies Am less than An, we are calling monotonically increasing, otherwise it is decreasing. So maybe similar to the BSR, we should give some name for this also. I mean, we cannot write this box every time, right? This box mean no two boxes are same, if you have seen. So let me give the name for this. So the name is monotone sequences, which means that are both increasing and decreasing. Okay. Now if you want to focus on increasing sequences, let me write here I. Monotonical sequence in R that are increasing, or maybe monotonically increasing sequences in R. See, that is why I am only writing just BR for bounded sequences. If I write B, S, increasing, decreasing, all that, it will become like this mess. So for that reason I am removing this S here, maybe MIR sufficient. Monotonically increasing sequences in R, that is what this notation is. Similarly, I can just write down, replace this I by D and then say monotonically decreasing sequence in R, and this is the definition for that. And what should you do just after defining just after realizing some special subset of any structure? Same thing that you have done for bounded sequence in R. Ask the following question: if I take two elements of SR that are elements of this, if I take two monotonically increasing sequences, is the sum monotonically increasing sequences. If A plus A comma B belongs to MDR, does it imply A plus B belongs to MDR? Same thing, A comma B belongs to MDR, does A dot B belongs to MDR? A belongs to MDR, does it imply minus A belongs to MDR? A belongs to MDR, that is nowhere 0, does it imply 1 by A belongs to MDR? If I say the same thing for MIR, it will be slightly boring, but the same thing that whatever I said for MDR, replace it with MIR and try to answer, try to understand something. And yes, that is where we end this session. So in this session what we have seen is, we have seen the notion of sequence in R, which are actually functions from a subset of R to R, but this subset is special, the first special subset of R, that is N. So these are functions from N to R that we are denoting by SR. Then what we have seen is the structure on R, induced structure on SR, the addition, the multiplication, additive inverse, multiplicate inverse, all these are all these have inspired SR to have some similar structure. So first three structures are straightforward, but for the multiplicate inverse there is a small issue here, there. So the problem was, for any element it might happen, it is not 0 everywhere, but it might be 0 somewhere. An may be 0 at some point of n belongs to n. So for that we do not know how to define 1 by A. So for this reason we said, for any element of SR, that means for any sequence in R that does not take 0 anywhere, then I can talk about 1 by A, this term 1 by A. What is it? By definition 1 by A of n is simply 1 by An. So that is about the structure on SR star. This star says none of the elements of n are mapped to 0. Then we said, whatever we have mentioned about, whatever we have done in R, that means we restricted our attention from every subset of R to bounded subset of R. The same reason this applies here also. So we restrict our attention from set of all sequences in R to bounded sequences in R. Then we have asked the following question. See, SR has some structure, BR is subset of SR. Does the operations on SR restrict to give operations on BR? Does addition of two bounded sequences is a bounded sequence, multiplication, minus A, 1 by A, all these, do they land in BR if they are starting from BR? That was one question. Then we realized maybe studying only that may not be interesting. So then we have seen that there are other kind of interesting sequences of the following type. If I take a sequence in n to R, n has some order already, that 3 less than 4, 5 less than 6, all like something like this. Then one can ask, what happened to the image? If m is less than n, what about am and an? Am is the image of m, an is the image of n. If m is less than n, an may not be relevant at all, you do not really know. If the case is that am is less than an, for every m comma n belongs to n, m less than n, then we called it to be increasing sequence. See, this should be true for every whatever I have written here, should be true for every m comma n of this property. If m is less than n, then am is equal to an, then we are calling as decreasing sequence. If m is less than n, then am is less than or equal to n, then we are calling increasing sequence. Then I asked, whatever the exercise that you have done for bounded sequences, you should do the same thing for MDR also. MDR, MIR are decreasing, increasing monotonic sequences in R. So you should do the same thing for that also. And after doing that, you should take a break. Tomorrow we will see some different subset of SR. Yeah, that's all.